In this video, I want to introduce elementary matrices. Let's go with the definition first. An elementary matrix is a square matrix which, upon multiplication on the left on a vector or matrix, is equivalent to performing an elementary row operation on that vector or matrix. The elementary matrix corresponding to any elementary row operation is obtained by performing that row operation on the m by m multiplicative identity matrix. Let's go ahead and recall that there are three types of elementary row operations, such as those used in Gaussian elimination. The three types are: 1. Multiply a row by a non-zero constant. 2. Switch two rows. Or 3. Add a multiple of one row to another row. Suppose that we've got this matrix A here. This is a 2 by 3 matrix in this particular case. To multiply by a square matrix on the left of this matrix, the matrix must have dimensions 2 by 2. Okay, since it has two rows, it better be a 2 by 2 if it's a square matrix multiplying on the left for it to make sense, right? Let's take example 1 here. Suppose that we want to multiply the second row of the matrix A by the factor 2. That would be a type 1 elementary row operation. First, perform this operation on the 2 by 2 multiplicative identity I sub 2 to yield E sub 1 equals 1002, as you see there. Then, if I go E1 times A, I get the second row of A multiplied by 2, nothing more. Okay? Which is the same result as performing the row operation on A. Let's take another example. What if we want to switch rows 1 and 2 of the matrix A? You first want to perform the switch on I2 to yield 0, 1, 1, 0. Then if I go E sub 2 times A, that has the effect of switching the two rows of A. Let's take a third example. This will be type 3. Suppose that we want to perform the row operation 3 times row 1 added to row 2 on the matrix A. We first perform the elementary row operation on I sub 2, and we would get the matrix 1, 0, 3, 1. Then, if I go E sub 3 times A, notice that this matrix has what? It has precisely the same as 3 times the row 1 added to row 2 on A. Very cool. All the results above would have been obtained by multiplying on any matrix with two rows. Here's a fact you want to remember. Every elementary matrix is invertible. Every elementary matrix is invertible, and we'll see why here. Let's talk about the type 1 elementary matrices. Suppose E1 is the m by m elementary matrix corresponding to the row operation on m by n matrices consisting of this: phi times row I replaces row I. In our previous symbolism, you have there phi times r sub I replaces r sub I. Then the inverse operation is clearly phi, multiplicative phi inverse, right? The reciprocal of phi, if you wish, times r sub I replaces r sub I. Example 4 then. In example 1 above, if I had E sub 1 was 1002, E1 inverse would be 1001 half. Now if you actually multiply those matrices together in either order, you will see you get 1001. Okay, should be pretty clear that those are going to be inverse operations here. These two are clearly going to invert each other's effects. Okay? Let's deal with type 2 elementary matrices, these corresponding to switching two rows. So suppose I have the operation where I want to switch row I and row J, and here's our symbolism for that we used. Actually, think about it here. This matrix, or this operation, is its own inverse, because if I have a matrix and I switch two rows, and then I apply that operation again, I would switch them right back to where they were before. So that means every type 2 elementary row matrix, or elementary matrix, is in fact its own inverse. So in example 2 that we had above, we had e sub 2 was 1 or 0, 1, 1, 0, and that's going to be exactly the same as its inverse. Okay, so obviously every type 2 elementary matrix is its own inverse. Here I've actually formally taken that product there, multiplying them together and noticing that I get the 2 by 2 identity. So these must actually be inverses of each other. So it's its own inverse, right? Okay, let's talk about type 3 elementary matrices. These correspond to what type of row operations? Where you're adding a multiple of one row to another row. And there I've got our symbolism there. Okay, in particular this means phi times row I added to row j replaces row j. Type 3 row operations are also invertible, since this operation minus phi times row I added to row j replacing row j will precisely cancel this operation above and vice versa. Okay? Let's take example 6 here. If we go back up to example 3, our example of a type 3 elementary matrix, I had adding 3 times the first row to the second row. That was corresponding to multiplying by e sub 3, 1, 0, 3, 1. And I claim its inverse is therefore going to be 1, 0, negative 3, 1. Okay? So that would be equivalent to adding negative 3 times the first row to the second row, and that should actually cancel out the first operation. Okay? So if you actually multiply these two matrices together, as you see, you'll end up with 1, 0, 0, 1, the 2 by 2 identity, proving that in fact these are inverses, multiplicative inverses. So it's clear that every single elementary matrix is invertible because they come in 3 different types, and all 3 of those types are invertible, so they're all invertible.